Hello, let us continue our lecture in organic chemistry, the basic principles and the fundamental aspects of organic chemistry. The last lecture we were discussing the reactive intermediates in organic chemistry and the type of bond fission in organic chemistry. We discussed about free radicals, carbocations, carbanions and carbenes in the last lecture. Now, let us start this lecture with the classification of reagents that are used in organic chemistry. Reagents can be by and large classified as free radicals, electrophiles and nucleophiles. The term philic essentially means affinity. So, electrophilic means species that are attracted to electrons. Species that are inherently electron deficient, which are attracted to electrons. So, likewise nucleophilic means species which are inherently electron rich in nature and they are attracted to positive centers or the nucleus of the reacting species. This is a very broad definition of the electrophile and nucleophile. Free radical is something we have already considered. This is an odd electron species having only 7 electrons around the carbon. Typically, we talk about free radicals which are tertiary free radical like the tertiary butyl radical, for example. We have already considered the free radicals in the last lecture. We will just discuss two types of reactions the free radicals can undergo. Free radicals can undergo addition to double and triple bonds. They can also undergo hydrogen abstraction reaction. If we consider a free radical R dot and it can undergo addition reaction to a double bond. They are essentially electron deficient in nature. So, they tend to add to electron rich double bonds, pi electron rich double bonds. In doing so, they form another free radical. If the free radical that is formed is a more stable free radical than the free radical that is reacting, then this reaction is a favorable reaction. Alternatively, free radicals can undergo hydrogen abstraction reaction. For example, the tertiary hydrogens in organic molecules can be abstracted by free radical because that generates the tertiary radical as the product or as the intermediate stage. So, this is the hydrogen abstraction reaction. The free radical essentially reacts with the CH bond, removes the hydrogen in the form of a hydrogen atom and produces a radical which is a tertiary radical. A very common reaction that is encountered is the triphenyl methyl radical, which can be generated, for example, by reacting a methyl radical. Methyl radical can be generated by photolyzing this type of azo compounds. So, in the process it produces a very stable trityl radical or triphenyl methyl radical. This is called trityl radical or triphenyl methyl radical. So, these are the two types of reactions generally encountered by free radicals in organic chemistry. Now, let us get back to the electrophiles and the nucleophiles. We have defined the electrophiles as electron deficient species. Let us start with the proton H plus. H plus is an electrophile. It can add to electron rich double bonds, for example, by protonation reaction. For example, it can react with the double bond to generate this carbonium ion or the carbocation can be generated. This is an addition reaction, addition of an electrophile to the double bond to produce the corresponding electrophilic carbonium ion or the carbocation. The double bond essentially reacts with the proton because a double bond is electron rich and proton is electron deficient, and in the process it generates a carbocation during the course of the reaction. Other electrophiles are, for example, Br plus, Cl plus, CH3, CO plus, for example. These are examples of electrophilic reagents in organic chemistry. How can one generate this electrophilic reagent? Even NO2 plus, for example, is an electrophilic reagent in organic chemistry. How do we generate these electrophilic reagents? One can take, for example, bromine and treat it with ferric bromide. Ferric bromide is Lewis acidic in nature. In the process, it produces the bromonium ion plus tetrabromoferrate as the product. You can take, for example, chlorine and react it with something like aluminum chloride. In the process, it produces chloronium tetrachloroaluminate. So, essentially the Lewis acidic nature of this reagent produces the corresponding electrophile by the heterolytic dissociation of the halogen-halogen bond, by the attachment of a halide ion onto the aluminum chloride or the ferric chloride as the reagent. Now, if you take sulfuric acid, concentrated sulfuric acid, and treat it with HNO3, for example, HNO3 is nothing but HONO2. The HONO2 undergoes initially a protonation because sulfuric acid is a stronger acid than nitric acid itself. So, this protonation essentially results in the formation of NO2 plus and water. The water is, of course, will be taken up by concentrated sulfuric acid. So, this is a standard way of producing the nitronium ion, which is an electrophilic reagent in organic chemistry. If you are wondering how to generate the acyl cation, this can also be generated by treating an acid chloride, acetyl chloride for example, when it is treated with aluminum chloride, essentially the aluminum chloride undergoes the substitution of the chlorine by this is of course resonance stabilized. One can write the resonance structure as this structure here. So, this is a acyl cation or acetyl cation is what we are referring to as the electrophile. Electrophiles can also be produced, alkyl carbonium ions are electrophiles for example. A methyl cation is an electrophile because it is electron deficient in nature, and that can also be generated by means of ionization process. If you take for example tertiary butyl chloride, and react it with aluminum chloride, you produce the corresponding carbonium ion which is an electrophile. So, generation of electrophile by treatment of a halide, particularly a tertiary halide, with a Lewis acid like aluminum chloride will generate the electrophilic reagent, which is the tertiary butyl cation as the electrophilic reagent. Now, let us move on to nucleophiles. Nucleophiles are electron rich species. So, they are essentially seeking the electropositive center or electron deficient center during the course of the reaction. Let us see some examples of nucleophiles. Water can be a nucleophile because it has two lone pairs of electron in the oxygen. So, it can act as a nucleophilic reagent in many organic reactions, particularly hydrolysis reactions are triggered by the nucleophilic attack of water on electron deficient center. Ammonia is a nucleophile for example, because of the presence of lone pair of electron on the nitrogen atom. So, in general amines, tertiary amines, secondary amines, primary amines, alcohols for example, they are all examples of nucleophiles because of the presence of electrons. One can classify them as mild nucleophiles, because if the nucleophile is not only electron rich, if it also possesses an anionic charge, then you would call them as strong nucleophiles. Strong nucleophiles are for example cyanide ion, hydroxide ion, alkoxide ion for example, phenoxide ion, azide ion for example. These are all typical examples of thiol for example, thiolate anion. Thiol is a very strong nucleophile, thiolate anion is a very strong nucleophile. Typically halide ions for example, fluoride, bromide, iodide, they are all fairly strong nucleophilic reagents in organic chemistry. They typically react with electron deficient center and undergo substitution reaction, addition reaction and so on. Let us see two types of reaction. One is the substitution reaction using a nucleophile. Suppose if you take tertiary butyl chloride and react it with, let us say for example sodium hydroxide, the chloride can be ionized and in its place the hydroxide can be substituted. So, essentially one can produce tertiary butyl alcohol as the product during the process of the substitution reaction. Here the carbon chlorine bond is polar. Under conditions of aqueous medium, the carbon chlorine bond can be ionized to produce a tertiary butyl cation. The OH minus can react with the tertiary butyl cation to produce the corresponding tertiary butyl alcohol. So, this is an example of a nucleophilic substitution reaction. Nucleophilic addition reaction can be classified by the addition of a nucleophile to a double bond, but the only condition is the double bond has to be electron deficient, the double bond. Now, let us consider two types of double bond. Let us consider ethylene double bond. Normally, this is electron rich because the pi electron is present in the system. However, suppose if I attach an electron withdrawing group, one or two electron withdrawing groups to the double bond, for example. Let us add one electron withdrawing group to the double bond. Nitro group is an electron withdrawing group, nitroethylene for example, or cyanoethylene, acrylonitrile, acrylic acid for example. These are all examples of double bond which are attached to electron withdrawing functional group. Because of the nature of the electron withdrawing functional group, you will have this kind of a effect resulting in a delta positive, delta negative kind of a, because the delta negative is stabilized by the electron withdrawing functional group. So, there is a polarization of the double bond which is already present in this type of system. So, the nucleophile, let us say for example OH minus, can essentially react with the double bond, and these are double bonds which are electron deficient double bonds in comparison to ethylene itself or butene itself, which are considered to be electron rich double bonds. So, the electron richness or the electron deficiency is only a relative term in terms of the relative reactivity pattern of the double bonds in this class of compounds. Having considered these three types of reagents, now let us classify the reactions of organic chemistry into various categories and see examples of the reactions of organic molecules. We have classified the reagents so far. Now, let us classify the types of reactions that one can anticipate or one can study in organic chemistry. So, we will talk about classification of organic reactions. Before we go into the classification of organic reaction, let me just say that in organic chemistry, you typically, let us say, represent a reaction mechanism by means of arrow pushing mechanisms. And the convention that is used in the arrow pushing is that you start the arrow from an electron rich center, let us say O minus, which is an electron rich center, push it towards the center which is electron deficient. Let us say for example, this carbon is an electron deficient center because of the polarization of the carbon chlorine bond. So, the arrow starts from the electron rich center and it is pushed towards the electron deficient center, pointing towards the electron deficient center. And if this is a leaving group, then this essentially means this chlorine leaves along with the bonding pair of electrons. So, in the process you produce methyl alcohol plus a chloride ion, for example. So, the arrow pushing mechanism essentially helps you to understand the kind of interaction between the reagent, in this particular case a nucleophile, with the substrate. In this particular case it is an electrophilic substrate because of the carbon chlorine bond, and it allows you to understand the kind of interactions that will be existing in this type of a reaction mechanism. So, organic reaction mechanisms are essentially an understanding of how bond is formed and bond is broken during the course of the reaction. So, an example of that is given here. This tells you there is a bond formed between the oxygen and the carbon, and a bond is being broken between the carbon and chlorine, because this reagent is now approaching this carbon and the chloride is leaving this carbon, for example. So, this is a typical way one represents the organic reaction mechanism by pushing arrows, and the convention is that the arrow starts from an electron rich center, and the arrowhead pointing at an electron deficient center. When I say center, I am just talking about atoms which are electron deficient and electron rich in nature. In this particular case, the oxygen atom is the electron rich because of the anionic charge and the lone pairs of electron that are present in the system, and the carbon, which is the electron deficient center, by virtue of having a halogen attached to it, it is already polarized in nature. So, having introduced the convention that is used for representing the organic reaction mechanism, let us look at some examples of organic reaction. One, substitution reaction. Substitution reaction can be classified into electrophilic substitution reaction or nucleophilic substitution reaction. In both of the electrophilic as well as nucleophilic, you have aliphatic and aromatic type. Here also you have aliphatic and aromatic type of electrophilic substitution reaction. So, you can have an aliphatic electrophilic substitution reaction, an aromatic electrophilic substitution reaction, an aliphatic nucleophilic substitution reaction, and an aromatic nucleophilic substitution reaction. Substitution reaction is essentially substituting a hydrogen or a functional group with another functional group. So, as a very general example, let us say a reagent X is reacting with RH. If the hydrogen is removed, let us not worry about how it is removed for the time being. You are essentially dealing with substituting a hydrogen with an X group, or if you are having a X group as a leaving group and Y is the entering group, this would also correspond to a substitution reaction. In other words, one group is substituted by another group, and depending upon this reagent here, this could be an electrophilic reagent or a nucleophilic reagent, and that would constitute a electrophilic substitution or a nucleophilic substitution. This substrate can be either aliphatic substrate or an aromatic substrate. So, here you can have either electrophile or nucleophile. Here you can have a aliphatic or aromatic substrate. Overall, the reaction is a substitution reaction. So, you can now understand an electrophilic aromatic or electrophilic aliphatic substitution reaction. Similarly, nucleophilic aromatic or nucleophilic aliphatic substitution reaction of this kind is what is generally talked about in substitution reaction. Let us take we already saw the nucleophilic substitution reaction. Here chloride is substituted by hydroxide. So, it is a nucleophilic substitution reaction. Here bromide is substituted by cyanide as a nucleophile. So, this is producing acetonitrile and sodium bromide. If you look at both the reaction, the chloride ion is displaced here and the bromide ion is displaced here, and this is the reactive species or the reagent that is used here. By virtue of having a OH minus or a Cn minus charge, these are nucleophilic reagents, and this is the electrophilic carbon. These are the electrophilic carbons. So, it is a nucleophilic substitution because the substituting reagent is a nucleophile in this particular case. So, these two examples will contribute essentially to aliphatic nucleophilic substitution reaction. Now, let us see one example of a aliphatic electrophilic substitution reaction. Now, let us take for example this is a special class of reaction. It is a silicon substituted, carbon silicon bond is what is being substituted here. If you treat this with a halogen, let us say for example bromine as a reagent, the carbon silicon bond is broken. So, silicon is the leaving group here, but it is leaving as a SiMe3 plus, and the reacting species is produce bromine. Bromine is the electrophile. It produces two compounds, trimethylsilyl bromide and ethyl bromide. Reaction is essentially an aliphatic reaction. The reagent is an electrophilic reagent, electron deficient reagent. So, it is an aliphatic electrophilic substitution reaction. Let us see one more example of the aliphatic electrophilic substitution reaction. Must be familiar with the iodoform reaction, for example. If you take a methyl ketone, let us say for example acetone, you can go all the way to tribromoacetone or triiodoacetone. If it is reacted with, for example, with bromine in this particular case, with either acid or base as a catalyst. Base is not a catalyst, but acid is as a catalyst. So, this is an example of a aliphatic electrophilic substitution reaction. The reagent is an electrophile here, bromine, and the carbon hydrogen bond is the hydrogen is the leaving group here. So, in the process it produces HBr as the product in this particular case. So, it is a sort of an autocatalytic reaction because the HBr that is produced will catalyze this reaction. Let us not worry too much about the reaction mechanism. What is important to understand is that the reagent is a electrophilic reagent, which is a halogen, which is an electron deficient because of its electronegativity. So, it reacts with the acetone. The replacement of the CH bond by bromine is what is the substitution reaction that we are talking about. This under basic condition is not stable. It will produce the bromoform, or if it is iodine used, the iodoform will be produced by means of a hydrolytic cleavage of the carbon-carbon bond in this particular system. So, these are examples of substitution reaction involving aliphatic reagents. In the case of aromatic substitution reaction, the most common reaction is the aromatic electrophilic substitution reaction, because aromatic rings are typically electron rich in nature. For example, if you take benzene, it is said to be electron rich because of the sextet of electrons that are present in the pi orbitals of benzene. So, let us take the example of substituting this hydrogen of benzene, which is same as every other hydrogen in benzene because it is a symmetrical molecule. The reagent is essentially an NO2 plus is the reagent produced by reaction of sulfuric acid with nitric acid. The combination of these two will essentially produce the NO2 plus. So, the two reagents that are reacting here are the NO2 plus and the hydrogen is released as a proton. So, you can see here the hydrogen is substituted by an electrophile. So, this is a electrophilic substitution reaction. Because it is carried out on an aromatic substrate, it is an aromatic electrophilic substitution reaction. Suppose if you want to do a nucleophilic aromatic substitution reaction, the nucleophile is electron rich. So, the aromatic ring has to be electron deficient in nature. How do we make aromatic ring as an electron deficient ring? By putting a large number of electron withdrawing functional group like the, for example, all the nitro groups in this molecule make it electron deficient in comparison to, for example, benzene or in comparison to nitrobenzene, and you have a good leaving group in the form of a fluoride ion. So, if you treat this with, let us say, OH minus, Cn minus, thiolate minus, for example, these are all nucleophiles. So, that constitute essentially a nucleophilic substitution reaction. Because it is carried out on an aromatic ring, it would correspond to an aromatic nucleophilic substitution reaction. So, the fluoride ion is being replaced by the OH, substituted by the OH, and this molecule is what is known as picric acid. Trinitrophenol is picric acid, highly bitter in nature. If you ever get the picric acid in your fingers, the finger will be bitter for several days. It gets absorbed under the skin and the bitterness lasts for a very long period of time. In the second example, a cyanide is produced, for example, with the loss of fluoride ion. In the last example, a sulfide is produced Now, you can ask the question, why not just to take chlorobenzene and do this kind of reaction? Chlorobenzene is not sufficiently electron deficient in nature to act as a substrate for the nucleophilic substitution reaction. Nevertheless, chlorobenzene under very harsh conditions can be made to react with sodium hydroxide to give phenol. This is more than 300 degrees centigrade. It can undergo phenol and sodium chloride. So, under very harsh conditions, one can push the reaction and make it to undergo this reaction. So, these examples I hope sufficiently illustrate the electrophilic substitution reaction as well as nucleophilic substitution reaction. This particular case SO3 is the electrophile producing a sulfonic acid derivative, for example. If you use ferric chloride and acetyl chloride, the electrophile that is generated is the CO plus. So, this will undergo electrophilic substitution reaction to produce acetophenone as the product. In all of these cases, proton is released during the course of the reaction. So, there are several examples of the substitution reaction that we have discussed during the course of the last 15 minutes or so. Let us move on to the second type of organic reaction, namely addition reaction. Addition reaction is essentially very simple by definition. Addition of two reagents across a double bond or a triple bond is known as the addition reaction. Here also one can classify this into electrophilic addition reaction, nucleophilic addition reaction. Normally aromatic compounds do not undergo addition reaction, they undergo substitution reaction because the double bonds are not typical double bonds, they are delocalized double bonds in the aromatic system. So, they cannot be considered like ethylene as an unsaturated compound. So, normally we are always talking about in the aliphatic compounds only this class of addition reactions in organic chemistry. Now, take the simple example of addition of hydrogen in the presence of a metal catalyst like nickel, for example. This will produce ethane as the reagent. Now, this is an example of an addition reaction. This is essentially a neutral H2 adding across a carbon-carbon double bond. This could be even a carbon-carbon triple bond, for example. Let us take this example. Here platinum or palladium or even nickel can be used for addition of the hydrogen. So, when it adds hydrogen, initially it produces an alkene, rather difficult to stop it at this alkene stage, essentially goes to the alkane, which is this particular alkane. In the phenyl propane is produced during the course of this reaction. So, these are simple addition reactions. It is hard to classify them as electrophilic or nucleophilic because the neutral hydrogen is what is adding in this type of a situation. On the other hand, if one adds bromine, for example, bromine water, decolorization of bromine water by ethylene is a very well known qualitative test in organic chemistry. Now, you are reacting with a electrophilic reagent. So, that produces dibromoethylene in this particular instance. Suppose if one adds water in the presence of an acid, when you say water in the presence of an acid, it is a hydronium ion that is being reactive species. This is also an electrophilic addition reaction. This will essentially initially produce this particular compound. You can see here the elements of water is being added across the carbon-carbon double bond in a sort of a regio-specific manner. The water molecule is given a specific color here, H2O is added, and this is a enol form. It does not exist in the enolic form. It goes to a ketone, which is this particular ketone. So, essentially you have added a molecule of water across a carbon-carbon triple bond to produce a ketone. This is also an electrophilic addition reaction. the reaction is triggered by the addition of a proton to the triple bond followed by attack of water onto the double bond, protonated double bond for example. So, the reactive species essentially is proton. In the absence of proton, water will not react with this reagent or with this substrate for example. This is electron rich triple bond. So, it has to be initially protonated to make a carbonium ion which reacts with water to produce the enol. Enol undergoes tautomerism to give the ketone as the product in this particular case. So, these are examples of aliphatic electrophilic addition reaction. Now, if you want to add a nucleophile to a double bond, as I mentioned earlier, the nucleophile has to add only to an electron deficient double bond. So, how do we make a double bond an electron deficient double bond? In comparison to ethylene, if you take this particular compound will be electron deficient methyl vinyl ketone, for the simple reason you have a resonance structure which is withdrawing the electron makes this carbon center as a electrophilic center. Now, nucleophile can add across this. So, if you react it with sodium hydroxide for example, it will essentially produce or if you add sodium cyanide for example in the presence of an aqueous acid, it will produce the cyanide will add across the carbon carbon double bond to produce the corresponding addition product. So, what you have done here is essentially taken a nucleophile, either the hydroxide or the cyanide here. This is also addition of water across a double bond, but then the reactive species is a hydroxy anion. Hydroxide anion is a reactive species. So, it is a nucleophile, and nucleophile is what is adding across the carbon carbon bond. Because of the electron deficient nature of the carbon carbon bond here, it undergoes the addition reaction in this particular manner to give the addition products which are nucleophilic addition across a carbon carbon double bond. There are also some addition reactions which are fairly advanced organic chemistry reactions which will be neutral in nature. I will give you one example of an addition reaction. These are also called cycloaddition reactions because they form cyclic compound during the course of the addition reaction. Let us take the example of ethylene. If ethylene undergoes photolysis in the UV region, in other words, if you shine light UV light on the ethylene molecule, two ethylene molecules undergo addition reaction to give cyclobutane as the product. So, what has happened is you write one more ethylene molecule beneath the other ethylene molecule, and essentially both of them are neutral compounds. There is no electrophilic or nucleophilic reagent involved here. The reaction proceeds through a excited state of the ethylene. One of the ethylene is excited to the higher electronically excited state, and the excited state of ethylene reacts with the ground state ethylene for example to produce a cyclobutene. So, this is an example of a photochemical cycloaddition reaction. What is the emphasis here? That this is an addition reaction, addition across carbon carbon double bond where the adding partner is also is carbon carbon double bond for example, leading to the formation. So, if you want to show it by means of a mechanism, this is how it is shown. This bond is essentially cleaved and a new carbon carbon bond is formed here, another new carbon carbon bond is formed here. So, these are the newly formed carbon carbon bond. You can see here this ethylene is added to the other ethylene. One more example we will see and then proceed further. If you take butadiene and react it with, for example, acrylic acid. This reaction is also an addition reaction. You look at this reaction carefully. A carbon-carbon bond is formed between these two carbons. The pi electron is shifted over here. This pi electron is involved in forming a carbon-carbon bond across this. So, this will essentially produce a cyclohexane derivative. This 4 carbon unit is a diene and this is a dienophile, and they undergo an addition, cycloaddition reaction to produce a cyclic compound. Since there are 4 carbons and 2 carbons involved, it is a 4 plus 2 cycloaddition reaction. So, it is a 4 plus 2 is 6. So, that is why a 6-membered ring is being formed in this particular instance. So, these are considered as neutral cycloaddition reaction because there are no electrophilic or nucleophilic reagents involved in any of this reaction. So, we are done with the addition reaction. We will move on to the next class of reaction, namely elimination reaction. Elimination reaction is just the opposite of addition reaction. If you can eliminate 2 units of functional group from a aliphatic compound, then you will end up with an unsaturated compound and the fragments of elimination. This is easily illustrated by taking this example. Here, if it is treated with strong alkali, under heating condition, the delta essentially means heat. What happens is, this already has a delta plus because of the inductive effect of the bromine. So, that makes this hydrogen acidic, makes the adjacent hydrogen also acidic, and as a result of that, an elimination reaction can happen under these conditions. The hydroxide ion is the base that is abstracting a proton. So, from the electron rich center you go to an electron deficient center, and this is essentially breaking a carbon hydrogen bond here, forming a double bond, and the bromine is lost as a bromide ion. So, you can see here an element of hydrogen bromide is being lost here. This will essentially produce ethylene. This is one of the ways of making ethylene in the laboratory. So, the overall reaction is ethylene is produced, sodium bromide is generated because you start with sodium hydroxide here, and water is the other product that is being produced. And this is an example of a elimination. Elimination reaction. One other elimination reaction we will see. If you take tertiary butyl alcohol and treat it with sulfuric acid or H plus, what will happen if you treat it with H plus? There are lone pairs of electron on the oxygen. So, the oxygen is going to be protonated with the simultaneous loss of a hydrogen from here. So, you eliminate water, in other words you do a dehydration reaction, produce the corresponding alkene. These are examples of elimination reaction. One can have a, this is what is known as beta elimination. It's beta elimination because this is a functional group which is being eliminated, This is the alpha carbon and this is the beta carbon. In other words, an element from the alpha carbon and another element from the beta carbon is eliminated. So, it is called beta elimination or 1,2 elimination. There are examples of alpha elimination known. If you take the chloroform and treat it with sodium hydroxide, chloroform, because of the presence of the 3 halogen on this carbon, this is a fairly acidic hydrogen. So, this hydrogen can be removed. So, the OH minus essentially removes this hydrogen. In the process, the electrons get pushed in this particular manner, producing a species known as dichlorocarbene. This is a general way of making dichlorocarbene, for example, using this. So, this is alpha elimination because both the groups are eliminated from the alpha position itself. Let us take one more example. This is methylene bromide. Methylene bromide has the structure which is this structure. When you react it with the zinc, for example, methylene bromide and methylene iodide can be reacted with the zinc. The zinc essentially gobbles up the 2 bromine atoms, producing zinc bromide in the process and produces a carbene as a reactive intermediate. The reaction proceeds essentially by initially zinc reacting with to produce an organo-zinc reagent like this. This will undergo elimination of the, this is also an example of an alpha elimination process, produces carbene directly by removal of 2 of the bromines by zinc. Zinc is an electropositive element, so it reduces the carbon bromine bond to produce the zinc bromide derivative here. This can eliminate zinc bromide as it is to give the carbene as the product in this particular instance. So, these are some examples of elimination reactions that we can appreciate in organic chemistry. There are also 1,4 eliminations known. Let us not concern ourselves with the 1,4 elimination for the time being. The last class of reaction is rearrangement reaction. This would be the 4th type. If you look at the Wohler's synthesis of urea, that is a fine example of a rearrangement reaction. Isocyanate is essentially on heating, undergoes rearrangement to give urea as the product. This is the probably the ever first rearrangement reaction that is known. Initially, you have a ammonium cyanate, which is the ionic substance, undergoing rearrangement to give a organic substrate, which is a neutral substrate, for example, neutral compound, which is urea. This is an example of a rearrangement reaction. In rearrangement reaction, atoms migrate from one position to another position. That is the most important thing. Here, for example, the hydrogens have migrated from the ammonium ion to the other nitrogen, and in fact, the cyanide ion is this particular ion. So, somewhere along the line the carbon nitrogen bond is broken and the carbon oxygen bond is formed during the course of the reaction. So, rearrangement reaction essentially involve migration of atoms from one carbon to another carbon. Let us quickly take a look at the rearrangement reaction. Here there is a rearrangement of the, if you treat it with an acid, essentially it will undergo rearrangement to give a more substituted olefin. Here there is a migration of a double bond from the, this is 1-butene, whereas this is 2-butene. So, migration of the double bond is also considered to be a rearrangement process. This can also be called as isomerization process. Carbonium ions are very prone to undergo rearrangement reaction. Last example we will look at here is that you take this as alcohol, which is a neopentyl alcohol. If you treat it with an acid, it produces neopentyl carbonium ion, which is a primary carbonium ion. The positive charge is on the carbon. So, you protonate the oxygen, remove a water molecule. This is a dehydration reaction is what we are talking. This is not a stable compound because this is a primary carbonium ion. So, there is a migration of the methyl group to the adjacent position because that will produce a tertiary carbonium ion, carbocation. This is a molecular rearrangement. You started with a highly branched trimethyl methyl derivative. Now you have a dimethyl ethyl derivative because there is a skeletal rearrangement that has taken place. So, these are some examples of organic classification of organic reaction. So, what we saw in this particular lecture is essentially the various types of attacking reagents, namely electrophiles and nucleophiles and free radicals, the various types of organic reactions under the classification of substitution, addition, elimination and rearrangement kind of reaction. Thank you very much for your kind attention.